Okay, so this problem is going to talk about the London Eye again, the Ferris wheel. It says use the Pythagorean theorem and the properties of right triangles to model an equation that fits the problem. Now, they give us a picture, which is very helpful. It says one of the cables that anchors the center of the London Eye Ferris wheel to the ground must be replaced. The cable is this cable right here, okay? So I'm going to call that X. All right. The center of the Ferris wheel is 69.5 meters above the ground. Okay, that's this line right here then, 69.5. So I'm going to draw a bigger triangle so you can see it better, hopefully. And so this is my X, this is the 69.5. And the second anchor on the ground is 23 meters from the base. So that's this distance right here, 23 meters. This is a right triangle, no matter how I drew it. And so that's the picture. They also in the picture have this labeled theta, that angle right there. So we'll keep that in mind. Approximately how long is the cable? So that's X. How long is this cable right here? We're going to figure that out with the Pythagorean theorem. And what is the angle of elevation? That's this angle right here we're talking about, from the ground up to the center of the Ferris wheel. So that's the angle of elevation, theta. So we need to find X and we need to find theta. To find X, we're going to use the Pythagorean theorem. So 23 squared plus 69.5 squared equals X squared, or the square root of 23 squared plus 69.5 squared equals X. You can put all this in your calculator at once. And so I did that earlier. Let's see. Nope, it's not that one. Well, I did it earlier. And what do we get? 73.2 meters for X. Okay? So that's how long the cable is. Length of the cable. So that's one answer right there. Now, we've got to find the angle of elevation. So we need to find this theta. So you could write tangent theta. We're going to use tangent because we know 69.5 and 23. Now, you might be saying, well, why don't you use sine? Because now you know what X is. You could, but it's better to use the exact values they give you. This one's rounded off, okay? So that was approximately 73.2. So it's better to go with one where you don't have to use something you rounded off. If you can, you can't always, but in this case we can. So, and tangent's very convenient because of the domain for tangent. So it's opposite, 69.5, over adjacent, which is 23. And so now we're going to solve that for theta. So we're going to use our inverse tangent button. So we're going to say theta is equal to inverse tangent of 69.5 over 23. Now, check your calculator. Put it in degrees, okay? They usually will put these in degrees as opposed to radians. They just do. It's, I guess, a more practical real-world application. Like if you were out on the job and you were saying, hey, anchor that cable, you would go by degrees, okay? They wouldn't put it in radians. Now, if you're in a math class and you're doing stuff, they might want it in radians, but I know here they're going to want it in degrees. So put your calculator in degrees and then type that in. Shouldn't be any problem. I'm getting theta to be approximately 71.7 degrees. I would go 1 decimal place. I think the book goes 2 decimal places. We'll have more information on that in chapter 8, but I would just go with that one. All right, that's problem